Hello everybody, here is another buffer calculation where we have a buffer that has a pH of 7.0 and a total concentration and a capacity of say 20 millimolar. So it's not a very strong capacity, not very high capacity buffer. And the pKa of this buffer is 7.0. We have a volume of 100 milliliter. And we want to calculate the amount of acid and base, respectively, that is in this buffer. Now, before we get started, of course, we do a sort of a reality check. We say we've got the Henderson-Hasselbalch equation, pH equals pKa minus log of the acid concentration divided by the base concentration, and I abbreviate it like that. And we said that if we've got the pH and the pKa, if they are the same, then we have the same ratio of acid and base. So if pH equals pKa, then we can conclude that the acid to base ratio is 1. And we can prove that. We just simply take the Henderson-Hasselbalch equation. So pH equals pKa minus log the acid concentration. And I just write it again, divided by the base concentration. We bring this to this side, we bring that to this side, and we've got log of the acid divided by the base equals pKa minus pH. We take both sides 10 to the power of, and then on the left-hand side, we've got the acid concentration over the base concentration equals, we have 10 to the power of pKa minus pH. And if we just simply plug in the numbers, we've got 10 to the power of 7 minus 7, and that of course is 0. So we've got 10 to the power of 0, and that would be 1. So we know that the pH, if the pH equals the pKa, the acid concentration is equal to the base concentration. And we can now calculate the total amount of moles in our buffer, so moles in buffer. And we know that we've got a capacity of 20 millimolar. So we've got 20 times 10 to the minus 3 mole per liter. And we've got a total of 100 milliliters. So we've got 100 times 10 to the minus 3 liter. The liter cancels out. And we've got a total of 2,000, or we can write it as 0.002 mole, which of course is the same as 2 millimole. So we know that the amount of the HA plus the base together gives us as 2 millimole. And we also know that the ratio is 1 to 1, so we can write HA over A minus equals 1, or we can say HA equals 1 times A. And we just simply take that and replace that here. So we've got A plus A minus equals 2 millimole and we have for A minus for the amount of base, we've got 1 millimole, and likewise for the amount of the acid, we also have 1 millimole. And together they give us the total amount of millimole of 2 millimole, and it's the right ratio that we have. Okay, so we've got 1 and 1 millimole of acid and base, and now we add to that a sodium hydroxide solution, and we do we add a high concentrated sodium hydroxide concentration, and before we do anything, we say how would the pH change. So adding OH minus would make the buffer more alkaline, and therefore we would expect that the pH would increase. But how much? Okay, let's calculate the number of moles that we have here of the sodium hydroxide. Mole OH minus that we have here. So we've got 10 mole per liter, and we've got 1 times 10 to the minus 3 liter. 1 milliliter, we cancels out, mole is in the right place, so that would give us a total amount of moles of 10 millimole. So we've got 10 millimoles of OH minus that we have, and which we are going to add to our buffer. Now we know that the HA plus OH minus will be neutralized, and we get A minus plus H2. So what we can do is we can, like we did in the previous example, we can say, okay, we've got HA, that was our starting, and we had 1 millimole. Likewise, the A minus, we also had 1 millimole. And now we add 10 millimole of the OH minus. So what do we get? For the HA, we get 1 millimole minus 10 millimole, which gives us negative 9 millimole. But wait a moment, negative 9 millimole, it doesn't make sense. We can't have a negative concentration or negative amount of the acid. So that's not possible. We couldn't put that into our Henderson-Hasselbalch equation because it's a negative number. So something is not right with the way we would treat this example. Instead, what we need to say is, we see very clearly that it doesn't work. And the way we can rectify that is that we say, okay, let's not worry so much about the HA, because the HA will be totally consumed. So HA will be consumed, will be fully, let's put it this way, fully consumed by and neutralized by the OH minus that we add. And we can actually calculate how much of the OH minus is left. So we can calculate OH minus, we had 10 millimole, and after addition of 1 millimole of the acid, we have 10 minus 1 equals 9 millimole of the OH minus. So we've got 9 millimole OH minus left. We don't need to worry about the base because that is relatively small and that doesn't contribute very much to the pH. So what we now need to do is we need to find out what is the pH, what is the pH of 9 millimole OH minus in a total of 101 milliliter. So we need to basically change the way we think about it and say the acid is all gone. What we have is the leftover of the base that has not been neutralized by the acid, so the leftover of the OH minus, which has not been neutralized by the acid, and that is what really counts now. So how do we do that? We just simply calculate the concentration of the OH minus that we've got left. So we've got 9 millimole, or we can say is equals 9 times 10 to the minus 3 mole. And we've got that in 101 milliliter, and we write this as 101 times 10 to the minus 3 liter. So that cancels out, and we have 9 over 101, which gives us roughly 0.089 molar. So that would be our concentration of the OH minus. Now we cannot directly calculate the pH, but we can calculate the pOH of that. So the pOH is given as the negative logarithm of the OH minus concentration, and that needs to be in molar, which we have. So we've got negative log of 0.089, and that gives us roughly a pH of +1, pOH of 1. Now we can convert the pOH into the pH, because we know that pH plus pOH equals 14. So the pH equals 14 minus 1, and the pH equals 13. And if we look at this, at our prediction, we said the pH will go up dramatically, or will go up because we add sodium hydroxide. And if we compare to the pOH that we would expect from this 10 molar sodium hydroxide, we find that the buffer really doesn't do anything. So buffer does not buffer anymore. And I put it like that. Buffer doesn't buffer anymore. And the reason for that is because the capacity of the buffer has been exceeded. The buffer just simply doesn't do anything anymore, and therefore we just simply can't use that buffer. It is basically dead. So this shows you how we can calculate this example where we add a huge amount of sodium hydroxide to a buffer, and that this will exceed the capacity. So I hope this makes sense, and thank you very much for watching.